Okay, in this video, we're going to look at the internal resistance of the batteries, essentially. And this is a thing that we've kind of ignored up until this point, and we essentially pretended like the circuits were essentially had no resistance within the battery, that only the resistance would exist outside of the battery, either in the wires that connect the battery or to the resistors that are connected to that battery. So I'm going to draw a picture. How would you draw a circuit diagram to show that the battery had resistance inside of it? So obviously, at this point, we're all pretty good at drawing the circuit diagrams. I'm going to draw a very simple one. Okay, so this is a large resistor. And what I'm going to do is to put the same thing, but a little smaller version. Okay, and while the big resistor would be called R, capital R, I would call this guy little r. So this is the same symbol that we use for the regular resistor, except it's usually a fairly small resistance that exists within the battery. Now, just to make sure it's clear that this is not a resistor that's just out in the circuit, but instead it's something that is physically inside of the battery, I'm going to draw a box around this. And this is what batteries have. They have a source of energy. That source of energy is called the EMF. The EMF is the internal electric potential. It's the internal electric potential, or it is the electric potential that is available to the charges inside of that battery when there's no current. Because the problem is that once the current starts to flow, the battery is made up of atoms, and the charges must pass from the one end of the battery to the terminal on the other end. That means they must physically pass through atoms. And of course, just like they face resistance in the wires, they're going to face resistance. So even though there's a chemical reaction that is providing energy to them, there's also obstacles in their way. And this is why the batteries will get warm. And you'll feel your phone getting warm for the same reason. When you use it a lot, you draw a lot of energy from the battery. That battery has an internal resistance, and over time, it will develop and become warmer and warmer. So the internal voltage is called the EMF, and I'll write this out in just a moment. But what I'd like to do is to add a voltmeter here. And so we can set up the relationship between these three variables. So generally, the voltmeters have either very large resistance or nearly infinite resistance. And so no current will flow down the path that has the voltmeter. So the current's going to be forced to stay in the circuit with the battery and with the large resistor that we have on this side. So once this circuit is up and operating and we have everything is all connected, current will begin to flow. And as a result, this voltage, which previously would have read the EMF of the battery, now that's going to read a less value, because some of the energy, while this energy is available, some of the energy is being lost as this portion of the battery heats up. So essentially, if we wanted to figure out what is the real voltage that is available to the external circuit, we would say, well, that would be equal to the EMF, but minus whatever we lose. So that little IR is referred to as the energy losses. That's what we're losing in energy per charge, is the current multiplied by that little tiny resistor. So this guy we would refer to as the external voltage. This is the EMF. EMF, I can't imagine you being asked to even define what it means, but it stands for electromotive force, meaning that this is what is providing the force or the push. Because again, the chemical the chemicals are releasing energy that can do work. They can apply a force to the charges that makes those charges begin to move. This is voltage lost in the battery. Those are called the IR losses. So with this equation, we can work out what the voltage is on this. And here's the thing about it. The voltage on the battery is actually going to change depending on what you have connected to it. Because the more current that passes through this battery, the more losses that there are going to be. So as you connect more and more things to it, not only are you dispensing more current, but then that's going to cause an even greater loss within the battery, which means that the external voltage, this is what's available to the outside part of the circuit. So everything going from here across to here and returning back to the other terminal of the battery. All of this is the external voltage. So when we measure the battery like this, we're getting the voltage on the battery, and then that is what is going to be available to the circuit on the outside here. Now, if you were to think about what would this look like in a graph, this is a really interesting thing. We can actually do a very simple experiment, not a complicated experiment, where we can actually measure that both internal resistance, the little r, and the EMF. Now, the EMF is actually, just for the record, is very easy to measure because all you have to do is take a voltmeter and put it to the terminals of a battery. Because remember, the voltmeter has a very, very large amount of resistance. So it's not going to draw any current, or at the very least, it's going to draw very, very little current. So when you just take the voltmeter and you touch it to the battery, you essentially, as long as there's no current flowing in it, that is the EMF of the battery. So if you think about what it would look like on a graph, this is what you would find. So if we make a, oops, here, sorry, so you can't even see what I'm looking at here. Let's make a graph of, you can do it either way. What I would suggest is that doing V versus I. So what you will find is that when there is no current, you actually get a reading on the voltmeter. It's going to look something like this. That is the EMF. The voltage when I equals 0. Okay, now what's going to happen is as the current increases, you're going to find that the battery is going to have a negative slope right here, right? And let's just think about this for a second. Look at the equation. V is equal to the EMF minus IR. That is the equation of this line. That's the equation of this line. So let me write the equation one more time, and let's think about where the various pieces are within this graph. So we have that V, the external voltage, is the internal voltage minus whatever internal losses that we have, right? So this is the y-intercept. And we have minus I times R, so look, that guy is the internal resistance. So that is the slope. That is the slope of this graph. So the little r would be simply done by collecting the data for several different current levels and then plotting it on the graph, taking the slope of that line, and that is the internal resistance. And it's typically very small for batteries. I mean, they're designed in such a way to minimize those losses. That's part of what making more efficient batteries is all about. So not terribly complicated, and we will definitely do a lab to try and see if we can measure the internal resistance of an actual real battery.